at the end as well. So to start off, thanks are in order. First to my advisor, Brendan, and also the rest of my committee, Dave, Sean, and Binhai. Also, thanks to Alex Tomescu, who was my supervisor during a visit to Helsinki at the University of Helsinki in Finland last year. Also feel free to get more pizza during the talk if you want. You're welcome to that. Also to all my collaborators during my PhD, so both on the projects that will be part of this dissertation, but also other projects that I've had, research projects I've had the opportunity to be part of throughout my PhD. A lot of those people are on the screen here or in person or on the Zoom, so thanks to all of you. Also thanks to the various research and writing groups that I've been able to be part of, to my friends and family, again, many of whom are here or on the Zoom, and also to the MSU Computer Science Department, both faculty and staff, and also fellow graduate students who we were able to support each other even during the pandemic. And also thank you to Cosmic Pizza. So if you buy a pizza from Cosmic, you get a letter that comes on the box. And if you can spell Cosmic, you get a free pizza. And so I was pretty sure that after 5 years, I would definitely have a lot of free pizzas. But as you can see, but a lot of C's, a lot of O's.
Quick question. Can you guys hear that lady talking?
Can you hear?
Sorry.
No. Can you not hear?
No, sorry. It's I unmuted one thing and unmuted you too. So I apologize so much.
No problem. Carry on. We'll just double check the chat right now. Great. People can hear. Back to it. So yeah. Sadly, only one full pizza after 5 years. I think that's the only regret of the PhD. Oh, also, I feel like, as you might notice, as we go through the talk, there was definitely an opportunity for me to incorporate these letters because we're going to talk a lot about copies of strings, but unfortunately, I did not think of that until today. So. Okay, so here is an outline of what I'll be talking about today. So we'll start with an introduction, including the motivation for the problem and the algorithmic problem of flow decomposition. And then we'll get into the content of the dissertation after that. So first we'll talk about some variations on flow decomposition. Then we'll talk about how we can improve the state of the art for solving minimum flow decomposition using an ILP. And then we'll get into some future work. So at a high level, this dissertation really only exists because of machines like these, which we call second generation sequencers or high throughput sequencers. And on one hand, these are really amazing machines because they can read the sequence of tiny DNA molecules very quickly and very cheaply. So when we first sequenced the first human genome, it took hundreds of millions of dollars and 10 years to do. But today, with machines like these, we're talking about sequencing genomes for just hundreds of dollars. But one catch is that these machines can only sequence short fragments of DNA. And so in order to reconstruct a full genome or even a full RNA transcript, which is the genetic sequence that we'll focus on today, we have to assemble these short sequences that we call reads. And so this is where computers come in because we might have millions of these reads and our output looks something like this. And this is also where computer scientists come in because we want to make sure that as we put these reads together, we're both getting the right answer. So that means reconstructing the true genome that was present or the true set of RNA transcripts. And we want it to take a reasonable amount of time. So as an introduction to my talk today, I will show how we can go from this real life problem of assembling reads to a well-defined algorithmic problem, which is flow decomposition. So in the basic version of the flow decomposition problem, we are given as input a flow network, which means that we have a start node labeled as S and an end node labeled as T. And for all other nodes, we have the property of conservation of flow. So that means that the total weight of all the edges or flow on all the edges pointing, for example, into A has to equal the total flow pointing out. So 20 into A equals the 20 pointing out, even though that's across two different edges. When we often think about flow networks as representing how water flows through pipes or cars flow over a road network, because if you think about 20 gallons of water reaching a junction in a pipe system, 20 has to flow out, or 20 cars reaching an intersection, those 20 cars then have to leave that intersection. But in this talk, we'll see how flow networks can also represent copies of strings or copies of genetic sequences. So in the problem of decomposing this flow, or the flow decomposition problem, we would like to output a set of paths along with a set of weights that perfectly decomposes the flow. So in this example, we can decompose this very simple flow network into 3 paths, one with weight 9, one with weight 11, and one with weight 987. And the natural optimization version of this is to look for the minimum number of paths possible that still perfectly decomposes the flow, paths and weights. So in terms of the algorithm side of this problem, it's already known that it's NP hard to solve minimum flow decomposition, even when the weights come from this sort of friendly set. But on the other hand, it's easy to find a solution that's not necessarily minimum, because every time we remove a path, S to T path with a given weight, we always maintain our flow conservation property. So for example, removing this weight 2 path, or removing this path with weight 2, we would still have the same amount of flow pointing into A as leaving A. And so a natural greedy strategy that's commonly used in practice is to do this, but at every step, we remove enough flow that we completely saturate an edge. So this same path with weight 9 will now eliminate this edge, and we can proceed, and we're guaranteed to not use any more than M, which is the number of edges paths. Okay, so let's see how we get one of these, get a flow decomposition problem from multi-assembly. And first, I want to make sure that we understand how we can represent strings as flow graphs, because that's a sort of key to this whole thing. So if in my nodes, I actually store either characters or sequences of characters, and then I paste those together by following my edges, then we can, for example, see the word sandwich as a source to sink or start to end path here. And if you were to sit here and look at this, you could probably find some other words as paths from the starting node, the $sign, to the ending node, the plus sign. But now, if I want to store not just the word sandwich, but the idea that I have 5 copies of it, I can label my edges with weight 5, and then say I also want, let's see if we get, we're having some weirdness in our projector for those not on Zoom, but maybe it will resolve itself. If it gets really bad, maybe I'll disconnect. Maybe yeah, I'll just try disconnecting from the like, well, let's just try presenting. Okay, this did not happen in my practice. So we got 5 copies of sandwich, but let's also add 8 copies of itch, 10 copies of audit, 10 copies of safety. And now, because I just added weighted paths at every step, I have a flow network, but I also have all that information about multiplicities of flow graphs or multiplicities of strings stored in this network. So now let's see how we can get one of these from when we're trying to reconstruct a certain type of genetic sequence called RNA transcripts. So even though all of our cells have the exact same DNA, the way in different cells or even in the same cell at different times, different genes might be turned on and more active than other genes. And so if we want to understand the connection between genetics and what cells are actually doing, we want to know which genes are turned on, which genes are turned off. And one way that we can do this is by measuring RNA transcripts, which are sort of intermediate step between the DNA sequence and the proteins, which are actually the things that do things in our cells. And so if we want to measure these RNA transcripts, let's see how they're made, try to understand them. So a gene, which here this gray bar is representing the sequence of the gene, so it's A's, C's, T's, and G's. The gene is made up of coding portions that we call exons, and I've highlighted in blue here, and also non-coding portions that are called introns. And it turns out that as our gene is being transcribed into RNA, sometimes through a process called alternative splicing, some of these exons can be skipped over. So the introns are always skipped over, but sometimes, so for example, in this second transcript, some exons are skipped, and here we have some other exons skipped. And so if we want to understand how we want to see what transcripts are present and what are their abundances, if we could just read their sequence, then it would be great. But what we actually get are these reads. And so the RNA transcript assembly problem is to recover the underlying transcripts and their abundances that generated the reads that we observe. And there are some similar problems, including viral quasi-species assembly and metagenomic assembly. Here, in both of these, there's some mixed set of genomes and abundances, and we just get the reads, and we want to recover what were the underlying genomes, whether they're viruses or bacteria or anything like that. So in general, we call all of these multi-assembly problems. When we have multiple underlying sequences, we want to reconstruct the sequences and their abundances. So for RNA transcripts, the main underlying idea is to reconstruct is what's called a splice graph. So just like the sandwich graph, or the graph that had the word sandwich in it before, here our nodes represent those exons in general, and edges represent adjacencies in a transcript between 2 exons. And so when we get our reads, and if we map a read to the edge, if a read overlaps 2 nodes, and then we map the read to that edge that represents the adjacency between those 2 nodes, and we proceed, and we've mapped all of our reads, we should, in theory, get a flow in this, what we call this splice graph, because it's representing those alternative splices. And then from this flow, if we decompose it into any set of paths and weights that perfectly decomposes it. So for example, say we take this path with weight 11, this orange path is with weight 3, and this green path with weight 2, then we will find some plausible set or possible set of transcripts and abundances that could have generated our reads. And in general, it's been empirically shown that the true transcripts, so in RNA transcript assembly, the true transcripts are almost always a minimum flow decomposition. So that's why we really want to solve this minimum flow decomposition problem. And in fact, flow decomposition is already used in practice for multi-assembly. This is a surely not non-exhaustive list of tools that are using flow decomposition as some part of their pipeline to go from those reads to the final RNA transcripts. But the issue is that even the most popular tools are only achieving a 50 to 60% precision on test data sets. And a similar story applies also for viral quasi-species tools, assembly tools. And so we've already seen, or what we've seen so far, is that minimum flow decomposition is a challenging NP-hard algorithmic problem that also lies at the heart of multi-assembly. And current multi-assembly tools are not getting the precision values that we would like them to. And so we ask, can variations on and algorithmic advances for minimum flow decomposition improve multi-assembly methods? And we specifically ask these 3 questions on the right. What if there are errors in the flow values? Can we use information from longer reads? Can we improve the state of the art for solving minimum flow decomposition exactly, so ensuring that we find the minimum? And I think of these 3 questions as actually representing 2 sort of lines of attack on this bigger problem. So the first 2 are thinking, if we can incorporate the information that the sequencers are already giving us in a more natural way, then we can hopefully get more accurate predictions, even if we have to use heuristics. Whereas this third question is directly addressing the issue that minimum flow decomposition is actually considered basically too hard to solve in practice. So we don't have all of the tools that I showed you on the last slide, they actually just solve this problem heuristically. But what if we can give a tool that solves minimum flow decomposition exactly, quickly enough that it can be used in practice? Okay, so in the next part, we will see 2 new variations on flow decomposition that we developed. So first, in many cases, when we get these splice graphs, these flow networks, they aren't a perfect flow. And a common way, so here, for example, we see that there's 19 flowing into A, but 24 leaving. And so a common way to deal with this is to correct to a flow in some optimal way, and then solve that using, say, a greedy strategy. And we asked, what if instead of doing that, we consider error bounds in a way, so intervals on our input flow, and we define what does flow decomposition mean for an interval graph like this? Because even though flow networks are very common in computer science, nobody had defined flow decomposition for an interval graph like this. And so what we found is that when we do define these intervals and decompose the flow relative to these intervals, rather than first correcting the flow and then using a greedy strategy to solve, then we do actually find smaller decompositions for RNA assembly data. And in our second project, we looked at defining or studying a version of the problem where we can take into account longer reads. So even regular sort of second generation sequencers may have reads that span more than one node. Or span, excuse me, it would be 3 or more nodes. So, but then it would be 2 edges. And so if we take those reads that are longer and encode them into our problem as what we call subpath constraints, and then we require that our flow decomposition not only perfectly explain the flow, but also cover every subpath constraint, then we ideally will have a more accurate decomposition that's closer to the ground truth transcripts. Because these longer reads are sort of like hints that to the true transcripts. And this idea, so a version of this is actually used in some of the top RNA assembly tools already. But the issue is that it had never been studied sort of on its own. And they just incorporate this sort of heuristically. So there had not been any study of specifically, are the subpath constraints increasing accuracy? Or is it just the other optimizations that these tools are including? And another interesting thing that came out of this project was that, so for the regular flow decomposition problem, there's always a way to decompose the flow into paths. In fact, in most cases, there are many ways to decompose the flow into paths. But as soon as we add these subpath constraints, we now could be given an instance that is not feasible, because our subpath constraints could contradict the flow, essentially contradict the flow that we're given. There could be no way to both satisfy the subpath constraints and also perfectly match the flow with paths. And when we first were thinking about this feasibility problem, is this FDSC instance feasible or not? It wasn't clear whether there would be a polynomial time algorithm to decide whether the instance was feasible. And what we found was that by moving from our full flow network with subpath constraints to a smaller network that just encoded the overlaps between the subpath constraints, because that was really the key to whether the input was feasible or not, then we could give a polynomial time algorithm to solve it. And so, yeah, all of this was in this paper from last year. All right, so now we will move on to the next part of the talk. Where we give a new ILP formulation for minimum flow decomposition. So actually, integer linear programming has already been used in some multi-assembly tools because it's a very natural way to express the idea of making discrete choices between will I include this path in my decomposition or that path? And for those who might not be familiar with integer linear programming or linear programming, I'll go through an example inspired by, I'm pretty sure the first time that I learned about linear programming, we had an example that had to do with producing beer steins or wine glasses. So I tried to throw back to that first experience for me. So suppose that I have the opportunity to go into, I'll do an example for those who don't know about integer linear programming. Not sure if I said that or not. So suppose I have the opportunity to go into a short-term business venture where I can produce drinking vessels and make a profit at the end of 3 months. So for example, if I make beer steins, then at the end of 3 months, I can sell all my beer steins for $200 and make $217. Similarly for wine glasses, if I make them at the end of my 3 months, I can sell them all and I make $125. But due to the cost of labor and supplies and whatnot, every month that I make them, which if I commit to making them, I have to make them all 3 months. Every month I have a certain cost associated with producing that item. So what I want to do is I want to maximize my profits, but I can't in any month go over my available funds. And so to formulate this as a ILP, integer linear program, first I need to define some integer decision variables. X1, X2, X3, and X4, where X1 is going to indicate if I assign X1 to be 1, then that means that I produce beer steins. If I assign X1 to be 0, I don't. Now I can express my entire problem. Now that I have these variables defined, I can express my entire problem using a set of linear constraints and also what we call an objective function. So here, my objective is to maximize my profit, which is the profit from each of my products that I produce, but I also can't go over my budget for each month. And so it turns out that for this specific problem, I do maximize my objective while also satisfying constraints. If I do make beer steins, I don't make wine glasses, I do make champagne flutes, and I do make teacups. So the reason that we care about ILPs is that, well, you've already seen we can express sort of business kind of problems using ILPs, but we can also express graph problems and lots of problems this way. And so there's been a lot of work that's gone into developing software that can solve these problems, meaning give these, once we write down our problem in this way, the software can find the answer in basically a surprisingly short time. So these should be really, really hard to solve, but this software can do well. And so that's why other people have already tried this. But the problem is that all the other previous ILPs for MFD have used an exponential number of variables. So, and this is because for every possible path through the graph from S to T, they create a new variable. And there are an exponential number of paths. There could be an exponential number of paths in the graph because, at every node, we can choose any of the edges and quickly we get to an exponential number of variables. And so even though the software is very well optimized, once we feed it formulation with an exponential number of variables, it's still not fast enough to be used in practice. And what these previous tools do is they just start ignoring paths. And so that means they're not actually solving minimum fluid decomposition. they are heuristics. They're not guaranteed to find the optimal solution. So it was an open question. Is there a polynomial size formulation into an ILP of minimum flow decomposition? And excitingly, the answer is yes, there is. So the kind of key idea is to express S to T paths sort of flexibly, express any S to T path just using one variable for each edge. And this idea was already known, hadn't been applied to minimum flow decomposition, but this idea was known in the operations research community previously. So had been used for problems like shortest path or other problems involving paths. And so luckily, we were able to work with a postdoc who, Fernando, who had, his background was in operations research. So he was able to help us a lot in this project. So thanks to Fernando. So let's try to get some intuition about how do we encode paths, S to T paths, just using one variable for each edge. So remember, our overall goal is to decompose this into weighted paths, but let's just first think about finding one single path. Kind of nice thing here is we're going to reuse the idea of conservation of flow, which already conservation of flow is a big part of our definition of these flow networks. And we can use conservation of flow here. So suppose this is the, let's say this is the ith path. We're gonna have some number of paths, but let's just say we're focusing on the ith path. So for the ith path, we're going to have m variables, which is one for each edge. So for example, from S to A, we have variable x, SA, and I, because it's the ith path. And this, as you might expect from our last example, it's a binary variable that will be 1 if we select that edge and 0 otherwise. Now, to make sure that we only select a path, an S to T path, and not like, we don't want to just allow ourselves to say select all the x's, like let all the x's be 1 or none of the x's. We want our constraints to make sure that we select an S to T path. So we can do this first by requiring that the total number of edges selected out of S is exactly 1. The total number selected into T is exactly 1. And then here's where the conservation of flow idea comes in. At every internal node, we require that the total number selected in is exactly the total number selected out. And so it's, for a graph without cycles, it's pretty easy to see that this will only allow us S to T paths. And then, so we would also need to define variables for the path weights. So, suppose I do select this specific red path here that does follow those constraints. I also have to assign it a weight to decompose the flow. So we can also add constraints to do that. And what I have been describing so far actually gives us a formulation for not specifically the MFD problem, but the KFD problem. So I specify a number of paths, and then we find a flow decomposition using exactly that number of paths. And so if I do have this sort of machine that solves KFD, then a naive way to use that to solve MFD would be to just start from k equals 1. Is there a flow decomposition using one path? If no, then I just need to move on to 2. Is there a decomposition with 2 paths? If no, I move on, etc. So that's the simple version, and that's what we have implemented so far. We could also be more clever. We could use binary search, or we could be a little more clever on our lower bound here as well. Okay, so great. We gave the first polynomial size ILP formulation for MFT, but does it run faster than the current best MFT solver? And fortunately, the answer is yes. We compared our ILP formulation to Toboggan, which is the only other minimum flow decomposition exact solver that exists currently, and also to Catfish, which is the state-of-the-art heuristic for minimum flow decomposition. And we, we'll see if it resolves itself. So we looked at 3 different data sets. So these all come from RNA sequencing data. And we divide these into by using the minimum flow decomposition size as a sort of proxy for difficulty. So the min K here is what is the size of a minimum decomposition of the instance. And so you can see that most of these, or all of these data sets are skewed toward those easier, smaller instances, but they all do have some bigger ones in the 16 to 20 range or the 21 and greater range. And so the thing that I want to point out is that our ILP formulation is able to solve 100% of the instances in under a minute. That's what this solved column is saying. Whereas Toboggan, once we get to those larger size instances, is only able to solve about half of the large ones in under a minute. Now, you might notice that Catfish also solves everything in under a minute, but remember, Catfish is a heuristic, so it's not guaranteed to find the optimal solution. And in fact, we can measure what's the difference because we have a MFT solver. What's the difference between what Catfish predicts and what the actual optimal is? And so you can see that Catfish is predicting multiple extra paths as we get to the larger instances. And so those are less likely to be the correct transcripts. Oh, and then I'll also point out that, so while we're clearly improving on the state of the art for those large instances, currently our implementation of the ILP is slower than Toboggan and also Catfish for the small instances. And I think that there is probably a relatively straightforward way to fix this. My guess is that Cplex has some startup cost that maybe we don't want to incur, like time to start up that maybe we don't want to incur if we can detect that it's a smaller instance. But this would be something to look at for future work. Yeah, so another benefit of our ILP formulation is that we can also include many practical variations that multi-assembly tools want to address. I'll focus specifically on subpath constraints, since we also worked on this in an earlier project. So it's not, in order to encode subpath constraints, what we can do, it's not super straightforward, but we can do it. What we can do is add another integer binary decision variable, Rij, that represents whether we cover subpath constraint J with path I. And it turns out that we can give inequality constraints that will ensure that this variable only gets to be One, if path I does in fact cover all of subpath constraint J. And then of course we require that every subpath constraint is in fact covered. And so all of this is presented in, or we will be presenting this paper next month. And there are some other variants that we can also address that I can talk about it in the Q&A as well, if anyone is interested. Okay, so that is all of the published, finished work included in this dissertation. To conclude, I wanted to talk a bit about some future work that is related to what we've already seen. So first off, with regards to algorithms for minimum flow decomposition, there's one gap that exists is in approximation algorithms. So I think of approximation algorithms as living somewhere between exact algorithms, which are those algorithms that we prove always find the optimal solution. So like the minimum, a minimum flow decomposition, and heuristic algorithms where we don't have any proof that there is a guarantee on how close they will be to optimal. And for approximation algorithms, this guarantee comes in the form of a multiplier oftentimes, or one way that it can come is as a multiplier. So for example, maybe we can give an algorithm that is guaranteed to be within 2 times the size of the optimal solution for flow decomposition. So one thing that was already known is that these greedy algorithms that we've discussed already can do at least as badly as root m times the size of an optimal decomposition. And in our work already, we have shown that we can increase this to m divided by log m. So basically, for the ratio. Basically what this means is we come up with a really evil instance that the greedy algorithms take a lot of paths to decompose, but we can show that there's actually a much smaller decomposition. Additionally, so this is kind of we might call this a negative result. It's saying that these existing algorithms can do at least as bad as this. In terms of giving approximation algorithms, that we can actually give that ratio that says it's going to do worse than this, it's going to do better than this. So far, well, previously there is not a very good approximation algorithm for MFD. So far, what we've found is that if we allow negative weights in the solution, so for example, say we use a path of weight -9 in our solution, then we can give an approximation algorithm, and it's guaranteed to be no bigger than the log of the largest flow value times the optimal solution. And so a goal would be to change this algorithm up a little bit so that it gets the same approximation ratio, even if we don't allow negative weights. So we return to the classic version of the problem. And then finally, another direction is to think about new variants. So one inspiration for this would be as technology changes, we have to accommodate that. One example being recently, those sequencing machines can now sequence RNA transcripts from a single cell, which could be useful rather than from a sample from a whole tissue, which could be useful for studying cancer because each cell might be mutated and behaving very differently from the cells around it. And so for that, often the data is quite noisy. So we might want to consider variants of the problem that can accommodate that noise. But another thing we can do is step back and think, what is the goal of RNA transcript assembly? Well, it's often to predict not, we don't really care about the transcripts in one single experiment. What we usually care about is what were the differences. What's the difference in gene expression between this experiment and that experiment? And what we do today is we assemble all the transcripts from experiment 1, we assemble all the transcripts from experiment 2, and then from those assembled transcripts, we find the difference. But what if instead we just go directly to the difference between the flow networks and we assemble the differentially expressed transcripts? And here, a negative weight path in the difference graph would mean that that transcript was overexpressed in experiment 2, and a positive path would be overexpressed in experiment 1. And so hopefully this difference graph can be simpler. We can avoid errors that we might make in each of these. And we already have an approximation algorithm for this negative version of the problem. So this is another promising direction that we plan to pursue. And oh, my picture's not looking good on with the weirdness. But double rainbow to thank you all for listening to me talk. So thanks, and yeah, I'll take questions.